Let's unpack this. We are diving into a universe that is, well, mostly invisible.
Right. A world governed by particles we can't see or touch or really detect easily at all.
We know dark matter is out there. I mean, it's 5 times more common than all the atoms are made of.
And yet, it's still the greatest mystery in physics.
It is the foundation of the cosmos, right?
Yeah.
It provides the gravitational scaffolding for galaxies to form.
Exactly. But it just refuses to interact with us. Our sources today take us right into the heart of the search, which is, well, it's fundamentally a technological race against cosmic noise.
So for this deep dive, our mission is to understand 2 deeply connected frontiers in this hunt for the invisible. On one side, we've got the Large Xenon Detector, or LZ, this colossal subterranean fortress designed to detect the hypothetical dark matter particle, the WIMP.
And on the other, you have experiments like COHERENT. They're trying to force the Standard Model's most famous ghost of the neutrino to reveal if it's secretly hiding new physics.
We've pulled high-level reports from CERN on the theoretical side, and then these incredibly detailed technical papers on the engineering.
They show the absolute extremes you have to go to. I mean, we're really looking for those aha moments that show us exactly how physicists are creating a space quiet enough and pure enough to listen for a single tiny invisible whisper.
So let's start where the search for new particles usually begins, at the highest energy machine on the planet.
The Large Hadron Collider at CERN.
It gave us the Higgs boson, but it's also been ground zero for the hunt for dark matter, often theorized as a WIMP, right? A weakly interacting massive particle.
That's right. The LHC strategy was basically the brute force approach. You smash protons together at just incredible energies and see if the explosion creates a WIMP.
Or some particle that would carry the dark force.
Exactly. The thinking was if WIMPs could be created at these energies, the LHC should have seen some trace by now. You know, maybe energy just vanishing from the collision, which would indicate an invisible particle had fled the detector.
But the results, the cupboard is bare. And, that feels like a failure. But our sources frame this as crucial intelligence. How does the absence of evidence actually narrow the field?
Oh, it's massive progress, actually. The dark matter theorists we're looking at, they confirm that the space of possibilities for WIMPs is dramatically smaller now than it was a decade ago.
So because we haven't seen it?
Right. If the WIMP existed within the mass and interaction ranges the LHC can probe, we should have seen it. Since we didn't, physicists are being forced to abandon or heavily modify the standard WIMP models.
So the LHC is telling us where dark matter isn't, which pushes theorists to ask, okay, if not a traditional WIMP, then what?
Precisely. And this is where the concept of the dark sector comes in.
Okay.
Instead of just one WIMP particle that interacts weakly, perhaps there's an entire parallel ecosystem of dark particles and forces.
And it would be connected to our visible universe by something exotic, like a hypothetical dark photon.
Exactly. And that shift in thinking means we can't just rely on creating dark matter anymore. We have to focus on catching the dark matter that's already streaming through us right now.
Which is the big transition from particle accelerators to direct detection. And that brings us to LZ, the Large Xenon Detector, built a mile deep in South Dakota.
LZ is one of the world's premier WIMP e-hunters. It's designed to look for these tiny nuclear recoils.
A WIMP slamming into a xenon nucleus. That's
the idea. So to maximize the chance of that collision, you just have to maximize the target mass.
And the scale is just... It's mind-boggling. The sources state the detector has a total mass of 10,000 kilograms of xenon.
10,000?
With 7,000 kilograms being actively monitored. But the final usable volume, the fiducial mass, is 5,600 kilograms. Why is there such a huge difference between what you have and what you can use?
That gap, that reduction from 7 tons to 5.6, that is the central engineering story. LZ is essentially a time projection chamber, a TPC, filled with liquid xenon. To find a WIMP, you need absolute quiet. And the minute you get near the walls of the detector, the steel, the wiring, the photodetectors, you introduce traces of natural radioactivity.
So the fiducial mass, the 5.6 tons, that's the volume that's far enough away from the walls to be genuinely clean.
Precisely. This whole thing relies on a core design feature, self-shielding.
The liquid xenon itself is the first line of defense.
It is. Think of it like walking into a massive pressurized water tank to escape a sandstorm.
So how effective is that liquid xenon shield?
Oh, extremely. The sources note that only about 2 centimeters of liquid xenon is enough to decrease the gamma ray background tenfold.
Wow.
And for harder to stop particles like neutrons, they need about 6 centimeters to get that same tenfold reduction. This naturally pushes the usable detection volume to the very center, away from all the radioactive edges.
And here's where it gets really interesting, because just having a big core isn't enough, right?
Yeah.
They actively surround that core with these veto systems to catch anything that tries to sneak in.
It's a remarkable dual-layer defense system. It's what allows them to push that usable volume up to the 5.6-ton fiducial mass.
So what's the first layer?
The inner layer is the X-skin. This is an instrumented buffer region over 2 tons of liquid xenon outside the main chamber, designed to tag any background particle that scatters near the edge.
And then the whole thing, the entire inner cryostat, sits inside this huge water tank filled with an outer detector. What's the special sauce in that?
It uses a gadolinium-loaded liquid scintillator, or GDLS.
Gadolinium.
Gadolinium is the key. When a neutron escapes the central xenon target, you need to be able to tag it instantly and reject the event. And gadolinium is chosen because it has this incredibly high cross-section for neutron capture.
So instead of relying on the rare chance a neutron hits a proton in the scintillator, which is inefficient.
Right. The gadolinium acts like a massive high-efficiency net. It significantly increases the neutron detection efficiency far beyond what you could get otherwise. The combination of that inner X-skin and the outer GDLS veto is what gets them that 5.6 tons. It would be impossible otherwise.
The engineering to get that level of shielding and purity is just phenomenal. But once you've built this ultra-quiet fortress, how on earth do you even calibrate it? You can't just stick a known radioactive source into the heart of the purest place on Earth.
That is the ultimate catch-22 of direct detection, yeah. The challenge is immense because the target sensitivity is, well, it's off the charts. You have to distinguish the WIMP signal, a nuclear recoil, or NR, from background noise.
Which is dominated by electron recoils, ERs, from natural radioactivity.
Exactly. And LZ needs to reject that ER background with 99.5% efficiency.
99.5, that sounds almost impossible, especially under the detector's extreme conditions. You've got the TPC running at minus 100 kilovolts.
Yeah, to generate the drift field. And then there's the purity spec. The required purity is truly staggering. They have to control contamination from krypton-85.
That's a beta emitter, right?
It is, with a 10.8-year half-life. And they have to control it to less than 0.015 parts per trillion, gram per gram.
Wait, 0.015 parts per trillion? I can't even visualize that.
It's like finding a tiny speck of dust in the total volume of several Olympic swimming pools. And achieving that in 10 tons of liquid is, well, it's arguably a bigger technological hurdle than just putting the detector a mile underground.
So back to calibration. To prove they can hit that 99.5% rejection rate, they have to map out exactly how the detector responds at very low energies. How do they do that?
They use a suite of these novel internal calibration methods. They actually disperse radioisotopes directly into the xenon for a short time.
Really?
Yeah. Their workhorse is krypton-83 maters. It has a well-known decay energy, about 41 keV, and a really short 1.8-hour half-life. So it's perfect for routine spatial monitoring, and then it quickly disappears.
And for that critical electron recoil discrimination, the false alarm zone, they use tritium.
Correct. The beta particle from tritium has an endpoint energy of about 18.6 keV, but the most probable energy is only around 3 keV.
Which is critical because that's exactly where the WIMP signal is expected to appear.
Precisely. You're using a known controlled type of low-energy electron recoil to perfectly map the false alarm zone. It lets you prove you can reject that noise at the exact energy level where a real dark matter hit would be.
But the WIMP signal is a nuclear recoil, an NR, not an electron recoil. So for that, they need neutrons.
Which means external sources.
So they have to bring radioactive sources right up to the detectors.
Right up to the exterior, yeah, through these specialized calibration tubes. And the engineering for that is, again, extreme.
What kind of sources are we talking?
It's a whole suite. AMLI, AMLI, YB, even a DB generator. Using external sources is the only way to measure the NR signal response. The yttrium-beryllium source, YB, is vital. It produces a sharp 4.5 keV NR endpoint right at the detection threshold.
And the sources note that this YB source generates such strong accompanying gamma radiation they have to deploy it with. What was it, 28 centimeters of tungsten shielding?
That's nearly a foot of solid metal.
Just to deploy a calibration source safely, it really shows the lengths they go to.
That level of detail shows you the technical barrier to entry in this field. It is a constant fight against every known form of radiation.
Let's shift a little bit because the WIMP search has been running parallel to a different hunt for an invisible particle.
The search for new physics in the neutrino world.
Exactly. Neutrinos aren't just background noise. They're a separate field of beyond the standard model BSM physics, being explored by experiments like COHERENT at Oak Ridge.
And the link between the two is central to this whole thing. Coherent observes this specific rare interaction called coherent elastic neutrino nucleus scattering, or CEVS.
Okay.
And crucially, CEVS generates low-energy nuclear recoils.
Which is the exact same type of physical signature a WIMP would produce.
Right. And this is why technology is developed for WIMP searches. These detectors, optimized for tiny nuclear recoils in materials like germanium or liquid argon, are perfect for CEVS detection. WIMP detectors are actually enabling neutrino physics.
So coherent isn't just confirming a known process, it's tightening the limits on theories that break the standard model entirely.
Absolutely. One major constraint they're working on involves what are called non-standard neutrino interactions, or NSI.
So, new forces.
Hypothetical new forces, yeah, mediated by unknown particles, maybe a potential Z-prime boson. If a Z-prime exists, it would subtly alter the CEVNS scattering they observe. Coherent data is being used right now to evaluate constraints on particles like that.
And they're also using this to hunt for a neutrino magnetic moment. That seems like a tiny thing, but finding that would be revolutionary, wouldn't it?
It would fundamentally break the standard model. The minimal standard model predicts a magnetic moment for the neutrino that is so ridiculously small, around 3.2 times 10 to the minus 19 Bohr magnetons. It's essentially unobservable.
A truly minuscule number.
It is. But many beyond the standard model theories suggest a value that's many, many orders of magnitude larger. So coherent experiments using germanium detectors are estimating their sensitivity to directly test these BSM predictions. They're trying to force the neutrino to reveal if it's more than just a simple standard model particle.
You know, this whole deep dive really boils down to how we hunt the invisible. On one hand, you have LZ building this gigantic, clean fortress, pushing purity and tech limits to find dark matter. On the other hand, you have Coherent using these same highly precise methods to see if the neutrino itself is hiding new BSM physics.
And in the end, both searches converge on the same physical and fundamental constraint. The real drama for LZ isn't just fighting cosmic rays or environmental radioactivity.
No.
The final, unavoidable, irreducible background noise that sets the ultimate sensitivity limit is caused by neutrinos from the sun.
We've built the perfect ghost trap, only to find the standard model itself is generating the final deafening noise floor.
Yeah, precisely. Solar neutrinos like the PP and boron-8 neutrinos are perfectly ordinary standard model particles, but they scatter just enough via CEVNS to create the very same low-energy nuclear recoils that LZ is hunting for. The world's best WIMP detector will eventually be entirely deafened by the standard model itself.
The search for dark matter and the search for new neutrino physics are converging in the same physical space. These low-energy nuclear recoils. The challenge isn't just finding a signal anymore.
No, it's finding a signal that isn't already mandated by the background noise of the universe. It really forces us to redefine what discovery even is.
Which raises an important question for you, the listener, to consider. For decades, physicists searched for particles and forces that were clear additions to our understanding. What happens when the next great discovery isn't a sudden clear detection, but is instead revealed only by finding a statistically significant absence of expected background? That's the boundary they are working on right now, searching not just for the invisible, but for the silence between the noise.